So this lecture, I'm going to talk about performance tuning, try to give you a little more insight into some of the choices that you may make that will impact how fast or how slowly things run. So by this point, you guys are already somewhat CUDA experts. You know how to write CUDA programs as well as the majority of programmers, because most people don't know CUDA yet. And what you want to do is now that you know how to write code, you want to have the skills to choose between different strategies so that you'll write code that will run faster. And depending on your application, different constraints, different limitations of the hardware may apply. And you have to develop both some knowledge about what's going on under the surface of the language and also some intuition about what kinds of things may be a problem for you. The other thing is, as in any programming, patterns are an important way of mapping a problem to a program. And there's certain sets of patterns for a data parallel kind of computation that tend to be effective strategies. So we'll give you a couple of examples and try to give you the background information so you can make good choices, both on G80 and for CUDA on multicore. So the first one of these that we have found to be a very, very important part of parallel programming in general and CUDA programming in particular is what we call computational thinking or computational reasoning. And this is the observation that probably the hardest part of parallel programming is before you start doing any of the programming. It's the process of understanding and analyzing your problem and mapping out what is the parallel structure, what is the opportunity for concurrency in your program. And I know you guys are all disciplined and careful programmers, so you always design your program before you start writing code. It's very important. It turns out to be critically important for parallel programming because you can really get yourself into a mess if you haven't thought about where the parallelism is going to be and how you're going to extract it and make it available to the hardware. So. Okay, so that's a good question. Let me just repeat the question for the remote people. When you're starting to try to write parallel GPU code, is it better to start from a sequential version of the program, a previously parallelized version, or from first principles in the algorithm and the approach? And let's see, I would say, I'd be interested to hear Wenmei's opinion also. I would say probably, your mileage may vary, your situation may vary, different situations may call for a different approach. The work that someone has done to parallelize something for a particular environment, say MPI, may be a different decomposition than you will want to do for the GPU. So actually the work that I would advocate doing is that sitting down with a pencil and paper and diagramming the problem, making sure you understand the flow of data and the flow of computation in the problem. And that also may help you to go back and look at the other parallel implementation and see if they did a good job of choices for how. Yeah, it's most time consuming, but if you do this work up front before you start to partition and write your code, you'll get a better result and it's even more time consuming if you do a bad decomposition and it's not fast and you have to go back and repair it later. That's a lot more time consuming. Always easier to do it right the first time.
Agreed.
Okay. But it really is a matter of discipline. It's very hard to resist the temptation to jump right in and start writing the code and getting something to run fast.
I think when you're possibly just starting out doing this, you might understand what some of the problems are too hard before you have to write code, so you can actually do a good job of designing the other without some experience.
Okay, so the comment is that as you're beginning CUDA program, you may not understand all the issues and you can't really necessarily do a good job of designing the algorithm. However, what I will say I think you can do a good job of is teasing apart and understanding the structure of the problem, and that is architecture independent. It's really the key is to think deeply about the problem you're trying to solve and what the inherent mathematical structure of the problem is, and then that leads you to some constraints that you probably aren't going to be able to change. But you could write code that would attempt to change those constraints and fail and run poorly. So this is the next part of the slide actually addresses the first question, which is understanding the relationship between the problem and the computational model, some of the computational tactics that may have been used in the past to solve the problem. And then the next phase is trying to map these computational strategies to the particular strengths and weaknesses of the computing devices, either the GPU or the multicore. And finally, if you've done all this well, the rest of it is fine optimizations, not gross optimization, and that is tuning the implementation to steer away from the fine-grained kind of limitations of the hardware. Should be a painless and almost effortless process. So some of the details of the hardware. How thread blocks are partitioned. If you have a block of threads, they will be executed as warps, and that's the way I prefer to think about it. They're not broken apart into warps like it's a chunk that's torn off. They're just consumed in the byte sizes and warps of the byte sizes. And the subdivision into warps, the thread IDs within each warp are consecutive and increasing. And warp 0 starts with thread 0, and as you go to warp 1, it's the warp size plus 1 and going on up. And this partitioning is always the same, so you can use this knowledge as you're designing your control flow. The only thing that is subject to change is the exact size of warps may change from generation to generation of hardware. It has not yet. All the hardware so far, the warp size is 32, but at this point I can guarantee that it will change. Into the design of a piece of hardware that will change the warp size. However, if you've written your code using symbolic constant of warp size, things should just work. And actually much of your code doesn't have to be sensitive to the warp size at all. So the question is, can I guarantee that warps will continue to exist rather than going away entirely? Let's see, guarantee is an absolute, so I can say I think so. I think I can guarantee it. So it's a fairly soft guarantee. But my expectation is that as long as we continue to build hardware that has what we call multiprocessors that try to consume threads in groups, there will be some logical grouping, some size of threads that get consumed in a byte. And that's really what the warp concept is. And the intention of that is to take advantage of coherence. And when similarly located threads are doing similar things, we can get our execution rate up quite a bit and get more efficiency by consuming them in warps. So the one thing, though, that you need to appreciate is there's no explicit or implicit ordering between the warps. The warps, since it's just a unit in which threads are consumed, if different threads are ready for execution, the warps may be scheduled for execution in any order. So if you have an algorithm that requires some particular ordering, or for every warp, every thread to get to a certain point, you need to use sync threads to make sure that they're lined up. They can get arbitrarily out of sync. So as you're building a program, unfortunately, it's not all floating point math. Sometimes there's flow of control, which is very inconvenient for processor designers. So the main performance concern that we see when you have a program with branching and decision-making is that the threads may diverge. And if different threads take different paths through the code, let's say in a single warp, then we serialize the execution of the different parts. We use an execution mask. We take the warp, and if you have if then else, you have two branches. All the code that is taken one branch gets executed in one cycle within the warp. All the code that is taken the other threads that have taken the other branch get executed in another cycle, and you execute them independently until they reconverge into the same path, and then the hardware will resynchronize them and start to execute them again in a single cycle. I think I mentioned this earlier. This supports a fully MIMD model. Every thread can have its own PC, and it can go its own way. And you could we have upwards of 12,000 threads that can be running at the same time, and you can take a 12,000 way branch in the first cycle, and they could all be doing something different really slowly, because every one of those instructions that's executed would have to take its own cycle, and nothing could be overlapped with any other threads. So one of the things to look for as you're doing your problem subdivision is how to avoid divergence. But you should notice that there's two kinds of divergence. If you have this execution divergence within a warp, then for that warp you need multiple cycles to execute the diverged code to handle both paths. But if you structure your code so that when there's divergence, it happens at warp granularity, or at least as far as is possible, the different warps can take different paths and it costs nothing, because it still takes a single cycle for each warp to execute, because all the threads within a given warp are running the same instruction. So there's two examples here, one of a piece of code that will cause divergence within a warp, and the second one where the branching is at a scale larger than the warp, so whole warps will take different branches, and so you don't pay the divergence cost. Does that make sense to everybody? Absolutely, yeah. The question is, does this apply to the branching that's associated with loops as well? Absolutely. Anytime you have a potential different code path for a thread, you want to have this picture in your mind of it's like street gangs. If they all stay together, they're more powerful. They'll wander off on their own. That's right. And it's not, it might cause trouble. It's a slight slowdown, but the slight slowdowns will add up. And if you look at a large CUDA program, different parts of the code may be limited by different things. Part of the time, if you have a lot of divergence, you spend more cycles, so you won't be able to keep the ALUs busy. Part of the time, you may be waiting on memory, or you may be dealing with register pressure, and you're doing a lot of spilling the local memory. And in that example of all those things, if you structure the code differently, if you have divergence, but you're also memory bound, and you correctly interleave and overlap those, then you don't pay any performance penalty, because you're not serializing those two costs. So I'm going to hand off to Wenmei here for a while, and I'll come back and join you later.
Okay, so just to give you more concrete understanding of the divergence problems, we're going to take you through some examples and take you through the divergence and ways to avoid divergence in these cases. So a very common pattern that the people using computing is reduction. So if you have a parallel execution and you generate a lot of results, at some point you may need to actually summarize them in some way. For example, if you have a large array, you want to know the sum of the array. That's a reduction. Okay, you generate one value out of a large number of elements. Or you want to figure out what is the maximum of the array. That's another way of summarizing the large number of values. Minimal. Okay, so there are all kinds of different things you can do, but they all belong in the same reduction pattern. The computation structure for generating all these summaries are pretty much the same. And typically, in the parallel implementation, you will recursively do it, essentially a divide and conquer. You just recursively divide the data array into smaller and smaller groups, and then you will do a summary, back up. So we do this all the time. In Olympics and any kind of tournament. Essentially, if you look at a tournament, it is a reduction process, and you go in with a large number of teams, and then each pair of teams fight, and half of the team fell by the wayside and half of the team forward, and essentially you're getting a maximum out of all the teams. So that's a reduction process. So we do that all the time. And in general, it takes log n steps for n elements, and that's exactly why in tournaments you always start with these pairs of teams, because as soon as you finish that first step, you get rid of half of the team. So it's a very, very fast way of going through all your data, and then the next step you half your data again. The next time you half your data again. So let's say if you have 1,000 teams, when you do this kind of reduction, the first step you get rid of 500 teams, right? The second step you get rid of another 250 teams. So with 1,000 teams, you should be able to get the maximum within how many steps? 10 steps, which is great. If you have 1,000,000 teams, right? Let's say one day we all get so good and we all go to the Olympics, and let's say I have 1,000,000 people, 1,000,000 team for the competition. No worries. The first day we get rid of 500,000, right? The second day we get off 1/4 It only takes 20 steps. So even if all 1,000,000 people are good enough for Olympics, we can still finish the whole game within 20 rounds. And if we can do a couple rounds a day, no worries. We can still finish the Olympics in time, right? So this is a very powerful mechanism. But the question is whether or not you will be able to do this efficiently on this particular architecture. Well, so let's do a vector reduction example. Let's assume that we're going to do an in-place reduction using the shared memory. So one of the first and foremost trick is to make sure that when you do reduction, you can actually use the on-chip memory for very fast access. Otherwise, just like what David is saying, if you start to have memory bottleneck, okay, if you start to run into memory bottleneck, unless you're very careful about overlapping the memory latencies with the branch divergence, they can actually add up. So in the end, you end up with very little performance. So a typical way of doing reduction in this kind of machine, or even in MPI, is that you would actually do a two-level kind of partition. You will partition the data. Let's say you have a large amount of data. Okay, you'll partition the data into chunks, and those chunks will fit into the shared memory. And you will do the reduction within the chunks. And then after the reduction, you will go back up and consolidate the data, and then eventually do the second level reduction by after the consolidation, so that the second level chunk can also fit into the shared memory. So we're going to do this in-place reduction, meaning that the original data will be actually all in the global memory. So shared memory, in this case, is really used as a scratch pad. That is, whatever you load into the shared memory, you will not expect to be able to use them later on. Okay? It's purely used, loaded into shared memory for you to manipulate even trash. Right? So with that assumption, you can do things very fast without worrying about preserving the data for future usage and so on. So that's why a lot of times when you look at the literature, people will call these shared memories scratch pad memories, meaning that whatever you load into the bit structure will probably be trash eventually. Okay? And each iteration will bring the partial sum vector closer to the sum. So after we load into the shared memory, we will do this round-off reduction. Okay? And eventually, the final answer will be eventually accumulated and eventually reach that element 0. Okay? And we do want to have a predictable location for the final answer. So let's take a quick look at this piece of code. Ideally, what I should do is I should pause for the moment and then start to have you craft that piece of code. Okay? And it actually is a good exercise. So when you go back, you should forget about everything I said and start to craft that piece of code and then think through. Then you should be able to reproduce everything I said in the lecture. Right? So that would be a good exercise for you after the lecture. So let's say we declare this partial sum, assuming that we're going to derive the sum of the array. Right? And now the piece of code that I'm talking about is the piece of code that does the chunk. Okay? So there's another piece of code that will actually divide things into chunks and then eventually gather up the results of the chunks and do the next chunk level. Right? So let's say we declare a partial sum array as shared, and then we go into the reduction loop. In every loop, we will actually generate pairwise sums. So in the first iteration, we'll take every pair of neighbors, okay, and generate a pair sum out of these pairs of neighbors. So in the end, we're going to have all the pair sums in the even elements, let's say, okay. And then the next iteration, we will go and take these even elements and generate pair sums. So we will generate, and then we'll deposit the elements, the sums, into the multiples of 4 positions, and then the multiple of 8 positions. Eventually, we will get only 1, right? And if you look at the code, what we're doing here is we're going to have a stride. Stride means that the distance between the pair of elements that we're going to do. In the very first step, we should start with 1 because they're all neighbors. They're all just 1 apart. And then the next iteration, we want the distance to be 2. They're all 2 apart, and then 4 apart, and 8 apart. Does that make sense? So that's why we start with stride 1. And in each iteration, we will check whether the stride is still less than the block dimension because we only have so many threads that we can use. And in this case, we're going to use 1 thread to produce a partial sum. Okay, so each iteration, we're going to use 1 of the threads to produce a pair sum. Yes?
My assumption might be wrong, but I don't understand the y-axis in the array, n times. Instead of, I have so many threads, partition the array, I have 1 million array,
Sure.
1,000 threads, partition the array,
Mhm.
and I am thread 0.
Yeah.
Take the first,
Yeah.
take this way, you access the array only once.
Yes.
Here you access n elements,
Yes.
n elements
Yeah.
divided
Yeah.
by 4.
Yeah. So that may well be a better approach. Okay, so but it does not illustrate the divergence. Okay, so the point is not necessarily the optimal algorithm. You may well be able to do better with an alternative. Okay, so in fact you probably will. So the stride is going to be multiplied by 2 every iteration, and then we do a sync thread at the beginning of the loop. The reason why we do the sync threads is because we are doing an in-place calculation. So every iteration is going to generate the input for the next iteration, right? We're going to generate a pairwise sum, and the pairwise sum is going to be used as the input for the next pairwise sum calculation. So we need to have a barrier synchronization before we enter the next iteration and making sure that the previous iteration has been done. And then within each iteration, what we're going to do is we're going to first test whether the thread ID, this T is the thread ID, the abbreviation for the thread ID, is satisfies is the multiple of 2 times thread. So essentially, this thing says is that at the beginning, if we have, let's say, all the n elements, we're doing pairwise sum. So we don't need to have all the threads. We only need to have 1 of the threads, 1 for each of the pair, right? And the next one, we only have 1 for each of effectively the 4 elements. So in each iteration, we'll progressively has fewer threads. This is exactly what Kyriakis was saying. In this case, you will have progressively fewer threads working on the partial sum. Whereas if you partition that into chunks and then just have the threads to continuous working, you should be able to get better utilization. But there are also other difficulties you need to overcome. That's why I said treat that as a homework. Yes.
I don't say that you would then use this algorithm once you have all your chunks, right? You have enough random elements left for me.
Yeah. At some point, you need to finish it up. Yeah.
I mean, it might not really give you that much in terms of runtime to do this at that point, but
Yeah.
that's when you probably decide you've already done the chunk.
Yeah. So that's exactly right. But work it out, and you'll see all the details exactly. So once you figure out the particular, you are the thread that has the honor to do that addition, in this current iteration. Then you will take the position of the position pointed to by your thread ID and the element that is stride away from you, okay? And you add those 2 elements and put it into the partial sum. So this is a relatively simple piece of code, okay? It looks pretty good and pretty benign. And if I look at it, without thinking about it, I say, well, this is probably as good as any other piece of code. And this is what David is saying. What we want to do is to actually give you enough intuition that, in the future, when you look at this piece of code, you immediately start to say, oh, there are a few things wrong about this piece of code, right? And so that you can begin to tell the difference between a high-performance piece of code and a low-performance piece of code. Oftentimes, they're not all that different. Oftentimes, they're just subtly different. So what's the, what does this piece of code really do? So the next picture shows the threads in action. So we will start with all the thread IDs, thread 0, thread 1, thread 2, all the way to up to thread, how many? 512. Remember, we can only have 512 threads in each block, and block is the unit of using shared memory. So only 512 of those threads, up to 512 of those threads, can see the same shared memory locations, right? Okay. So what the algorithm does is that essentially we have one thread that corresponds to each data element position, and right from the first iteration, we're going to use only half of the threads. Okay, we're only using half of the threads, and we're using the even threads to produce the pairwise sum and put them into the even positions. Okay, and then we have 1/4 of the threads working that will produce the partial sums into the multiples of 2s and multiple of 4s, and then a multiple of 8s until we exhaust all the levels. So this is precisely what David was talking about. You will have divergence of thread execution even right from the beginning, because you will have threads that will not execute the addition, and you'll have threads that execute the addition. For threads the way the GAD hardware will handle this case is they will first execute through the threads, let's say, that does the addition. So in that pass, all the other threads will still see that instruction, but they will not take effect. Okay, the hardware will suppress the execution result. They're still going to go through the motions, but they're not going to be able to generate any visible result. So that's the first pass. And then it will come back and go through the same code, but different paths, and execute the threads that are not going to take it, that are not doing the addition. So eventually they will merge back at the end of the if construct. And that's where they all get back together and go to the next iteration. And there was a question about loops. I think John asked the loops. So the divergence of loops happens if the loop bound is dependent on the thread ID. So if some of the loops will take more iterations than others, then each pass will go through the loops that take a different number of iterations until they're all finished. Okay, so that's how this divergence is going to work out.
Why is the secret required? I said that it's part of automatic secret that conversion point.
Yeah.
So since it's conversion, why do you use secret?
Oh, no, it's different. Okay, so the convergence happens at the end of it. Yeah, but that's only to merge all the control back together. The sync thread is still there because of the data production. Remember that let's say you could have a situation where the data may or may not have completely finished, right? So these two are different. In this case, in some of the hardware, you may get lucky, okay? But in general, you should separate out the data synchronization. You shouldn't assume that the control synchronization will implicitly synchronize all the threads with data, okay? So there's some observations here. In each iteration, two control paths will sequentially traverse. That's what what I already said. And the threads will perform addition, and threads that do not, and they would the threads that do not perform the addition may cause extra cycle depending on the implementation of divergence. So no more than half of the threads will be executing at any time. And this is kind of an interesting concept here. Essentially, when you look at it, you say, what's the problem? There are really two problems. One is, you will take some extra cycles to handle the ones that do the addition and the ones that do not. Okay, so that's obvious. The other kind of drawback is a little bit less obvious. If you have a total amount of work, this is going back to what Kirk was trying to say. If you have a computation where each warp is starting with half of the threads, really doing useful work, and then progressively getting fewer and fewer, then remember warps are the scheduling units. So you will essentially take, if you think about it, you will be taking a large number of warps, but each warp will be doing only partial amount of, having partial amount of productivity. So essentially you'll have a large number of workers, but those workers are not being fully productive. Okay. So, but each time you execute these warps, you will still need to bring them into the hardware. They will still fully occupy the execution resources. It's just that they're not taking effect. Okay. So remember this point, and when we come back to when we come to a different piece of code, you will start to see that subtle difference. Yes.
So essentially, you think of this code as running like n log n instead of n is what you want, or n word, because it's essentially n log n word.
It is no. That's what you're saying. Yes. I'm not sure if it's n log. Yeah. Right. It's definitely more than log n. So the question is whether it's proportional to n. I don't think so. I think it's more like 2 log n or something. But in this case, it should be up to 2 log n rather than n log n. Right. Yeah, I think so. Because every iteration becomes potentially 2 passes. So you're doubling the execution time. Right. Up to. Yes.
So does the divergence happen at the if, or does it restart from the top of the?
No, if divergence will be we don't know for sure, but conceptually you can think about it from if, and the convergence will be the end of it. Yeah. And if you could have nested if statements.
Yeah, and then you're taking that.
And so they may actually have different divergence points. So you can have, essentially it's probably a stack-based kind of approach where you, okay. So if you look at a better implementation, again, at this point I should have paused and have used to start to craft a piece of code that is better, that works better, right? So this piece of code, it looks almost identical to the other piece of code, but it has a little bit of a difference. First of all, you will start the stride rather than from 1, you will start the stride from the maximum, okay? So rather than starting from the neighbors, now we're starting from 2 elements that are almost halfway away from each other. Okay, so we will start with the block dimension x, and then we'll test whether the stride is still greater than 1. Okay, and when we get down to stride 1, we know we're done. Okay, and then every time we iterate, we will divide the stride by 2. Okay? And for those of you who are familiar with integer arithmetic, divide by 2 is really shift to the right by 1 bit, right? So so this loop essentially allows us to to go down and actually execute do the sums from the farthest possible neighbor halfway around the Earth, and then we do the synchron. Then eventually we would finish the iteration. So what we're going to do is we're going to say, well, look at the thread ID, and if the thread ID is less than the distance, and that is we're right from the beginning we're only going to use half of the threads, and the half of the threads are going to be the lower half of the space. Remember, we still need to have only one thread per per pair, right? So we're using the lower part of the thread ID to calculate these pairs. Okay, so we're essentially sucking those farther values into the lower half. And so once we did this, we finish the calculation. We take 2 halves of the data. We take all these pair sums and put them into the lower part positions. So by the time we go to the next iteration, all the input values will be in the lower part half, and we partition it into half and do the same thing. Okay. So what's the big deal? You're still using half of the thread to start with. You're still having these potential divergence. But if you look at it, what it really does is you will have thread 0 that will do the pair of 0, and let's say in this case if there are 32 to start, then you will do 0 and 16 and put that into position 0. The good part is that all the threads that are going to be doing addition in the first iteration will be neighboring threads, because thread 1 is going to be doing the same addition but between element 1 and 17. So all the threads with neighboring IDs will now be either doing addition or not doing addition. So you get rid of the divergence, because remember the warps are formed by consecutive threads, right? Threads with consecutive IDs. So if I look at the first iteration, I will have all the consecutive threads that will be doing addition, and then I'll have the other half of the threads not doing addition. And you say, oh, there's still divergence, and that's what David was saying. Divergence across warps do not cost you anything. Okay, the hardware will just do a single pass for the warps that do the addition, and hardware will also just do a single pass on all the warps that don't do addition. Make sense? The second one that is a little bit more subtle. Now we have warps that do things, and then we have warps that don't do things. So remember, warps are scheduling units. So whenever a warp is now being scheduled into the hardware, it will be fully productive, or it will not execute instruction. Therefore, it will just go away very quickly. You will not be just hanging in there and waiting for some of these threads to finish and some of the threads to do nothing, right? So now you have actually, from scheduling point of view, the scheduler will be able to pick productive warps and spend all the execution resources on the productive warps. Okay, so that's why you have a more subtle effect of getting more execution efficiency out of this. Make sense? Okay. Yes. The warp size is actually 32. So what I'm showing here is a very small case. And on the other hand, you're raising I think you just raised an important point here. That is, at some point, you're still going to go down below 32. Once you go down below 32, you will still have divergence. Okay, you still have lower half of your threads and the upper half of your threads in the warp that will still diverge, and that will happen in the last 5 iterations of the loop. So let's say if you have 512, you're going to have 9 iterations. The first 4 iterations will be non-divergent, and the last 5 iterations will be. And typically, what people do is they will actually unroll the last 5 iterations so that you can avoid divergence. But I'm not going to worry about that for the moment.
In this case, you don't really care about anything since you're not beyond this.
Right.
So you could just do the same thing in the threads that you're not using.
Right.
And what yours.
Say again.
So
The last iteration. Right. Yes.
You don't care what those other 16 threads are doing.
Exactly.
They do the exact same thing.
Yes, they could.
And then you don't have those.
That's exactly what a unrolled piece of code would do. So what you said is the right objective. And what people typically do is to unroll the loop so that essentially the other half of the warps will be doing the same thing. Okay, rather than using the if construct and the loop construct. Okay, very good. So this is divergence. And the next consideration that is of first order effect in this machine is the memory layout. Okay, and we have so far we have kind of glossed over the nature of global memory accesses. Okay, and remember, I think there was Koryakis who asked this question about the cache efficiency. And in the CPU, when you access sequential data, the cache will load multiple bytes in the sequential locations, therefore get efficiency out of the memory accesses. And the question was whether or not there's something similar in the CPU, in the GPUs that will achieve the same effect. If that's not very familiar to you, don't worry, because I'm going to go through the basic concepts here anyway. So let's go back and review what the C memory layout, which is row major, is about. So let's say if I have a 2-dimensional array, and the way the array elements are stored in the global memory is going to be row major. That is, all the elements in a row will stick together, and then the next row will come right after the first row, and the next row will come right after the second row, and so on. So this is how you will store all the 2-dimensional array elements into a linearized memory. So there is a concept of memory coalescing for precisely the reason of efficiency considerations. What happens in dynamic RAM or DRAM, which is the technology that we use for the global memory here, is that invariably it's more efficient every time when you go to the memory system. It's much more efficient for you to request a large number of bytes than just a small number of bytes. The reason is these things all take time to set up. So when people build these memories and the buses, they actually need to have certain hardware latency. And so what they do is they will typically get a bunch of bytes out of the storage. And the bus will be set up so that if you work out the transfer of the first byte, it will be a lot easier for you to transfer more bytes. Okay, so this is almost like the following. Let's say if you need to go to the gas station and buy a Coke, okay, and the nearest gas station is on the corner of University and 6th Street, I believe. And so if let's say Lauren wants to have a glass of Coke, so she will go and buy it. So that's she will walk all the way over and come back with that Coke, right? And then later on David wants a glass of Coke, so he will walk over and get another cup. And this whole thing is very slow. And what could be much better is that if Lauren walks over and she knows that David will need a cup of Coke, they will have the clerk to produce 2 cups of Coke, which is a lot faster than that walking distance. And if she comes back with 2 cups, the whole process is only slightly longer. Then both of them sequentially go to the memory and then go to the gas station, not memory, and fetch those Cokes. The only addition is the slight more time for the shop to give you another cup, right? So this is pretty much the same thing with memory accesses. And so if you look at the way the hardware works, I actually don't know exactly how the hardware works, by the way. This is one of the things I have to admit that it's a little bit magical to me. But from the programmer point of view, you will actually have 2 different possible access patterns in a 2-dimensional array, and one is more efficient than the other. This is all you need to know. So let's take the first access pattern. Let's say if each thread is accessing a 2-dimensional array in the horizontal direction. Okay? So this will be the M array, right, in the matrix multiplication. Each thread is going to go horizontally when it does the dot product. Make sense? And the other access pattern will be the N array, where each thread is going to come down in a column and do the dot product. Which one do you think is more efficient in the memory system? Any volunteers? Who thinks that the first horizontal direction is more efficient in the machine? How many of you? Makes sense. How many of you think the second access pattern is more efficient? Makes more sense. Okay, so here's the reason. The reason is, remember the warp, right? There are 32 threads that are all kind of moving forward at the same time. So even though when you look at the code is going in the horizontal direction. So the traditional thinking is I'm making accesses, in a sequential way, right? The reality is every clock cycle, okay, when you execute the thing, you're really executing 32 of those threads. And so in the same time, 32 of those locations in the vertical direction are actually being requested out to the memory system. So these simultaneous requests are actually made to locations that are actually quite far away from each other in the layout. Because you will be accessing the beginning of the first row, the beginning of the second row, the beginning of the third row. Remember the row major layout? That these locations are actually quite far away from each other in the memory. So you're not accessing anything close to each other in that batch of accesses that the hardware is going to make on behalf of all the 32 threads at the same time. Whereas in the vertical direction, at every moment, the hardware is going to see 32 of those threads, and they are actually all accessing nearby locations. In fact, they're all accessing neighboring locations. So that's the reason why the hardware has opportunity to say, oh, here are 32 requests to the memory that are all to the neighboring locations. That's when Lawrence light bulb come up and say, I'm going to grab that cup of Coke for David. And that will score big. Okay? So that's the reason why the second access is much more efficient. It appears to be counterintuitive because you always think about loops going horizontal direction, accessing neighboring elements sequentially will be the more efficient access. But the fact that there's so many other threads with you, and the fact that every iteration of your access is going to be at the same time with multiple other threads, that makes a difference in this hardware. So that's why in this access is not what we call a non-coalesced access. That is, the hardware will not be able to actually recognize the opportunity and grab all the neighboring bytes for you. Yes?
Yeah. You don't get an advantage out of the fact that the next step might already be there, or your data is going to be anything or else.
Very good. Okay, so remember, those accesses are actually, the answer is I don't know. Okay, I actually, this is the part where the hardware becomes a little bit magic to me. I can tell you what I guess it does because I actually have done some experimentation and there's some things. But I think the better answer is from David.
Well, I think I described earlier that the caches don't provide much reuse. There's enough things in flight that you want to look at the caches as staging. So the data that you're reading for a single cycle is taking up a cache line. The data that you're reading for the cycle after that is taking up a cache line. And each cache line is going to be evicted right after it's used. So it's possible if you're not reading a lot of other stuff, that the data will still be there, but you are likely reading a lot of other stuff. And really the big effect that you're dealing with the coalescing and with optimizing your reads is that, again, this is a graphics processor built to do graphics. We build a high-performance memory system that is very wide and very fast. So the minimum size of memory read that is efficient with the DRAMs is maybe 256 bytes, or bigger than that, and getting bigger all the time because the width of the DRAMs is increasing. So if you're reading some value, and out of your 256 bytes, you're only using 4 bytes, you're using one floating point number, the rest of that read is just wasted. You never get that back. Out of your 80 gigabytes per second, you just wasted 90% of it, and you never get that. That time is gone. That time is passed. So it's not so much about reuse, but as in consuming everything that you've taken. It's like a buffet. You took a plateful. Take all you want, but eat all you take. Okay?
You said that you would swap the word out once this word had done something that we slow, like access from memory. So in the first access pattern, would you be fetching more than just one element, or would you be fetching a lot of elements for all the threads and 7 threads and then fetch the next one before that word was,
That's in the detail of coalescing, right?
Yeah, and that's if your data is not coalescible, you're going to have to do all of those reads, and you're going to issue all those sequential reads, and that's exactly the case where you're going to guarantee that there's no reuse.
But if it's coalesced, they may be combined, right? That's what you're asking, right?
right. I guess I don't exactly understand.
But the first order effect is to know that once you coalesce, it's much, much better than the other one. So how much better? Yeah.
The first one is, I still believe that the first one is going to be a cache parental exception.
Mhm.
The second one is always
That's right.
vector wise exception.
Yeah.
The proposal now, which one of the operation you want to do? You have multiplication or transpose.
Right.
Is that the specific operation?
That's the next slide. Yeah, you're just ahead of me. Okay, and yes.
How much can vectors allow
Mhm.
the efficiency of coalescing?
Yeah, you need to have align access. So if you are off alignment, we did notice it's not complete loss, but you'll have degradation. But most of the data structure should be aligned, hopefully.
So you start the array after the word boundary.
Yes, yeah, especially the word boundaries. If it's out of word boundaries, it's really bad.
The multiple word boundaries is better.
Yeah. But that effect is less severe than the non-word align. Yeah, now you're asking this is the reason why I said up front that I don't know exactly how this is designed. In fact, you shouldn't have to know as a programmer, but you should know that there's a first order effect of coalesced or non-coalesced sequences. Okay? So this is for your benefit. And when you go back and look at these accesses, if you do a vertical access, you're going to see that all the threads will be accessing neighboring locations, and then the next step, all the threads will be accessing sequential locations. But if it's horizontal access, all the threads will be actually accessing non-sequential locations in the first time period, and then all the threads will be accessing non-sequential locations in the next time period. This is what Carolyn was asking. If you have some kind of caching, you could have preserved some information on chip somewhere for this batch. So, but that's in the hardware design. And what David is saying is, do not count on it because there's probably not enough cache space for you to preserve that. Okay? So how do you deal with this situation? Most people use shared memory to essentially get a coalescing effect automatically. So this is what John was asking. When I have a matrix multiplication, the natural access order for M is horizontal for each thread. So how do I transpose the array? Do I do some kind of fundamental adjustment to the data structure? And with shared memory, the problem is actually quite easy to deal with. Remember, in a tiled algorithm, we're going to load one tile of M and one tile of N. So when we load the tiles, we don't need to strictly adhere to the computation order that we're later going to use. We can actually load the tiles in the vertical direction, because you just need to have each thread to load each element. Whether they go here or there, it doesn't matter, as long as the entire tile gets loaded. So that's why, if you look at the tiled algorithm implementation, sure enough, for both M and N, they are all going to be loaded in the thread code. You will see that all the neighboring threads will be loading horizontal neighboring elements. That's why when you look at the matrix multiplication code, there's something very subtle yesterday that I was afraid that one of you was going to ask. The loading of MDS and NDS are exactly the same in terms of thread ID, even though the access patterns are different, right? So this was the reason why we're loading them exactly the same way, because they are both coalesced, okay, in that access pattern. Okay, so let's kind of review this a little bit. In the tiled multiply, we're going to load one tile, and then we're going to do the computation on that one tile, and then we'll move on to the next tile. And we do have these tiling size effects that we were talking about yesterday. And so remember, I was saying that when we do the tile multiplication until we get to 16 by 16, the memory access is such a bottleneck, even with coalescing. In fact, the way we did the tile loading was actually coalesced. Okay, but until we get to 16 by 16, the memory is still going to be saturated enough that none of these other things matter. And this is what David was talking about at the beginning. When you tune the performance, you need to make sure that you're hitting the right bottleneck. If the bottleneck is not taken care of, everything else you do won't matter. And this goes. I'm running behind just a little bit. But I think it's still a worthwhile story to tell, because that will probably help you to remember this for the rest of your life. There was this fellow who got drunk, right? So he went to summer school. He worked really hard. On Friday he went home and he decided to go to the bar and have a good time. So he got really drunk and he went back to the house and he was fumbling and trying to get a key, and then he slipped and the key dropped into the thorny bush next to the front door. And he's very drunk, and he tried to reach for the key, and then he got it thrown in the finger and it's out. And then so he immediately rushed across the street and started to look for his keys. So here comes a policeman, see a drunkard, and kind of looking around very suspicious, and say, "What are you doing?" And the guy said, "Oh, I'm looking for the key to my door." And the police officer said, "Okay, so let me help you. But let me see your ID." And the guy said, "Okay, yeah." So, "Okay, so you look here, that's fine. So let me look for the key with you." And then, "Where did you drop it?" The guy said, "Back there." And I said, "Why are you looking here?" He said, "Well, but it's a lot easier to look here. There's no thorny bush here, right?" So make sure that you're hitting the right problem, even though it could be a hard problem. Hit it, right? Don't hit the easy problem that it's not a problem here. So there are several things that can become a bottleneck, and you really need to know which are the bottleneck there is. And one of the immediate step that you're going to take for a lot of these programs is that you're going to immediately allocate some of these variables into the registers, right, and share memory, so that you can eliminate a lot of memory accesses to the global memory. And when you move these variables into registers, there is something that you really have to keep in mind for this machine. This machine is very powerful in a sense. That is, the register file, there's a very large amount of registers in each shared memory, in the order of 10,000 for G80 implementation. It could be even bigger in the future, or smaller for that matter. And all these registers are actually partitioned for thread execution on a dynamic basis. So that is, if you have, let's say, 1,000 threads, then each thread could be using about 10 registers. But if you have, let's say, 2 threads, they can use a lot of those registers. Okay, so you can choose to have very coarse-grained threads that use a lot of registers, but few of them. But you can also choose to use a large number of threads, maximum number of threads, but each one use up to about 10 registers. Okay, in this design. So this gives you a lot of good flexibility and that you can tune the granularity of your parallelism. So it's a very powerful design. In fact, when I came from the CPU world into this world, that's one of the first things I noticed, because the CPUs tend to give you 32 registers, and they tend to give you more registers for each thread, even if you needed more. Right? So this is actually a very nice feature to have. On the other hand, precisely because these partitions are dynamic, you can run into problems without knowing it. Okay, so this is an example where, let's say if I have, if each thread uses registers in such a way that I can have 4 blocks to occupy the entire register file. And if I just increase the register usage by 1 in each thread, and therefore I increase the total usage of the block by a certain amount, even if I increase it by a very small amount, I immediately kick out one of the thread blocks because I can no longer accommodate all the 4. Okay? And this often happens in a fairly sharp basis, because as soon as you hit that limit, you immediately lose a whole block of threads, and you really can feel it. You lose a lot of parallelism when that happens. So this is something that you always need to keep in mind. Once you exceed the limitation, and if that's a limitation that will limit the number of threads in a SN, you will start to see some fairly sharp effects. I'm going to show you some graphs, probably at Friday morning. So for the matrix multiplication example, if you do the calculation, you will see that for 200, for the number of threads that you're going to use and the number of registers you're going to have, you're going to be able to tell that, well, if I want 256 threads in a block, then when I use 10 registers, I would use 2,560 registers. And 3 of those blocks will essentially use almost up to the 8, this is the exact number for G80, 8,192. So I can accommodate the 3 blocks plus a little bit change. However, if I increase the number of registers to 11, then I immediately exceeded that limitation with only 3 blocks. So therefore, I drop immediately to 2 blocks, and I lose 1/3 of my parallelism right there. Okay. So, I'm not going to go over this slide because I already talked about it. This whole dynamic partitioning can be a very good friend of yours because you have a lot of control over how you do the parallelism, but then you need to be aware when you hit these limitations. So, I'm probably going to skip this slide because this is a little more subtle, but if you're interested in this kind of trade-off, maybe come and talk to me. There's a trade-off between instruction level and thread level parallelism. And precisely because we have so many threads, if we have more parallelism in each thread, we may not need to have as many threads as in the case where we don't have a lot of parallelism within each thread. So if you work out a scheduling algorithm, it's actually very significant. So sometimes we can actually do some trade-off. By doing some loop and rolling within a thread, by using more registers, we can create more parallelism within the thread that we don't need to switch across more threads, as many threads as we would need in the other case. And it's actually a very significant trade-off. But this is a trade-off that we do not recommend you do by hand. This should be done by the tools in the future. So that's why I'm going to skip this slide. But it's something that you probably just want to keep in the back of your mind. And the resource allocation, I just illustrated that when you exceed the registered file limit, you're going to actually have a situation where one of the blocks will not be admitted into the SAM. So now, at this point, I'd like to use the example to show you several other trade-offs that people do beyond what you learned so far, even in the case of matrix multiplication. One of the important trade-offs is the amount of work you do in each thread. Okay. So far, we have essentially say it as a given that every thread calculates one element of the output array for the multiplication, but it really doesn't have to be. And you could have each thread to calculate 2 elements, 4 elements, 3 elements for that matter. And so if you do that, you increase the amount of work that each thread does. In fact, you can also potentially increase the parallelism within the thread. Okay, because you may be requesting memory for more than one output element, and you can better tolerate some of these latencies. And also, you can have more efficiency. In this case, let's say if each thread is going to process 2 elements, one from each of the neighboring tiles, let's say these 2 elements will be processed by the same thread, then both threads can actually share the global access to n, because both elements require the same row of n. So this is also where you can get efficiency. You can actually eliminate the entire access to the row of n by accessing it once and use it twice on these 2 threads. And this is typically done by storing that value in the register file. Okay, using a loadable register, but then you save even more of your memory accesses. And even with tiled algorithm, this can be still usable because you can save some access to the shear memory, and shear memory access still takes cycles. It takes instruction slots. It still takes load instructions to happen. So this is one of the trade-offs that you're going to see. And the highest performance matrix multiplication implementations use multiple elements. They don't just do one. Okay, and this is one of the dimensions that you're going to have to deal with. Prefetching. Prefetching is a very, very important skill in computer science altogether. Okay, no matter what processor you do, it's an important technique. And you do prefetching all the time. Okay. Whenever, let's say, you need to call a taxi in a big city, one way to do it is, you go downstairs or something from your condo, and then you try to see if there's a taxi on the street, right? And, you have an unpredictable amount of time, when you call a taxi that way. Or before you go downstairs, you call a taxi cab. If you use valet parking in hotels, you know the better way is to call them before you go downstairs, right? So they will fetch the car while you come down for the elevator. So whenever you can actually overlap the latency with something else, you can always get ahead, right? And prefetching here does the same thing. In the original code, what we do is we load the current tile into the shared memory, and then we synchronize, and then we compute the current tile, and then we synchronize before we go back to fetch the next tile. So we have fetch, we have compute, we have fetch, we have compute. The reason why we did all right with that is because there are other warps, okay, there are other blocks that also need to do fetch, compute, fetch, compute. So if we somehow kind of slip them off from each other, then you will hopefully always find some threads, some blocks that can do compute, right, while others are doing load, right? So that's how multi-threading works. However, in those cases, you do need to have more blocks, a lot of blocks that you can do this, right? And if you do prefetching, that's another trade-off that you can do. Within a thread, what you can do is you can actually load the next tile. And so you load the current tile, and then you immediately load the next tile. Okay, so you're loading 2 tiles at the same time, right? And right after you load the next tile, while you are still loading the next tile, you will do the next tile. You will do the compute. So the compute can happen right while you're loading the next tile. So by the time you go back, you will likely see the next tile already in the shared memory, but then you'll be loading the yet next tile. So you will be doing within the same thread block. You will do the loading of the next tile while you do the current compute. And this typically requires twice the amount of shared memory because loading the next tile should not overwrite the data of the current tile. So you need to have 2, and the professional term for this is double buffering, right? And so you will need to, double the usage of the shared memory, and sometimes you need to use more registers for this approach. But on the other hand, it's less likely you're going to be waiting for data whenever the processor is looking for work to do. So again, you could be using fewer blocks and achieve the same level of performance. So how you balance out depends on the exact design of the hardware. Finally, there is an instruction mix consideration here. This is a consideration I always talk about last because this is going to be most likely the next generation of improvement, and it will become even less important. In the current generation, the processor will have to consume instruction cycle for floating point operations as well as branches or address calculations and so on. So if you have an address calculation instruction where you have a branch instruction, it's as expensive as a floating point instruction. And more importantly, the hardware does need to take time to crank through the address calculation while it cannot process floating point operation. So you would end up in a situation where even though the processor is busy, the floating point units may not be fully occupied. Okay. So a typical way to deal with this problem is loop and rolling. So instead of having a loop on top here, I would essentially do the multiplication and add, but I would execute the increment of the counter and then the branch instruction and the test and the branch instruction. So the execution of these things will actually make the hardware execution, the floating point execution unit not totally occupied. What I can easily do is I can unroll the loop. Let's say when I have a block size of 16, I will just unroll it totally 16 times. So I will end up with 16 of these terms. Okay? It looks ugly. It does look ugly, trust me. But the benefit is I no longer have a branch instruction in every iteration. I don't need to increment the counter every iteration. And also, I have replaced the address calculation as constants that will fit into the addressing mode of the instructions for those of you who are interested in lower level details. So all these effects added together allows me to essentially fully utilize the floating point unit. Okay? Yes? Yes. Very good question. So let me answer that question. So yes, it is. In fact, I think the first time when David and I taught this course, I asked him exactly that question. Loop unrolling is one of the easiest optimizations that you can make in the compiler. However, it's one of the hardest optimizations to control properly. So the trick is for the compiler to know when to unroll and how many times to unroll. Okay, and that's the reason why this optimization is probably not in the production compiler yet. However, this is actually what I was going to say next. This is also one of those aspects that will probably be either in the compiler, so that will be one way of fixing this problem. The compiler will do this automatically for you, so you don't worry about it. Or the hardware may eventually become what we call a multi-issue hardware, where the integers and the floating point can be simultaneously issued to the execution unit, so that even though they're integer operations, the floating point unit will still be fully utilized. Okay, so once one of those two things happen, the programmer shouldn't have to worry about it from the source code level. But in the current generation, I still teach this job.
The compiler right now does actually accept unrolled fragments, so you can include in your source code fragment that says.
Oh, good. But you need to tell the compiler exactly how many times?
I think so.
Yeah, so that gets around the control problem, right? You still control it, yes. But effectively, conceptually, if you did that, pragma, you're conceptually doing this. So at least you know exactly what it's supposed to be doing. So with the removal of branch instructions and so on, you actually end up using fewer registers when you unroll, because you no longer use a register to hold a loop counter. So this is actually counterintuitive, because a lot of you who have experience with CPU loop unrolling, typically when you unroll loops in CPU, you will end up using more registers. And if you're interested in knowing why the difference exists, I will explain to you in person, but I don't want to take it up for the whole class, because it's one of those details that are not going to affect people's ability to program effectively on this machine. So you will end up using fewer registers. You will end up making better use of your hardware unit. That's why unrolling on this machine, on the G80, the one that you're using, can actually make a tremendous amount of difference. So if you look at the performance graph, now the performance graph of the tile algorithm should make sense. So unroll. So we just applied that unrolling to the innermost loop and did more than double the performance. Okay, for this piece of hardware, precisely because we're not fully utilizing the floating point unit. Okay? So that's pretty much it. You always will wonder, no matter what you do, you always will wonder how close are we to the best performance. The answer is you probably will never know. So I'm going to show you some graphs tomorrow and then Friday again, that oftentimes humans will not be able to find the real optimal performance, even given a known space of optimization. The reason is all these factors: loop unrolling, granularity adjustment, tile length size. Right? We have already talked about several dimensions of variables that we can change. Right? All these things, and unrolling factors, all these things essentially combine and generate a very large search space. All the combinational values give you a potential code configuration. And I will show you humans constantly fail to find the best configuration. And that's the reason why we produce a space search group, tool in our group to actually identify the best value. And I'm going to talk a little bit about it on Friday. And that's yet another thing that is probably going to go into the tool chain at some point and simplify the programming efforts for you guys. So this is one quick example where the human, this is one part that when we offer the course at one point, this is what the human finds, and this is what the automatic tool finds. And there's actually a sizable difference of performance. So, but in order to go from here to here, you actually need to suffer some losses before you can go here. So you will not be able to, that's why the human didn't find it. The human sees some degradation of performance along the way and just didn't look far enough to find the best performance. So there are also other plausible ideas, and even in the best configuration, using all the techniques that I talked about today, we're getting about 120 gigaflops on the machine that you'll be using today. But we already know that you can get close to 200 gigaflops if you do one more trick. Okay? So if you do get that by the end of Thursday, I'd like to know, because I'd like to enlist you for some future tasks. Okay? So that's pretty much what I want to talk about, and this is just a summary of the detractors of performance, and you should understand all these now, but it's a good summary to have when you think about these problems. So it's just kind of a slide for you to to remind you of some of these factors to keep in mind. And so at this point, we're running late, but we still will take a break. So let's take a 5-minute break and get back, and we'll continue with floating point. Okay?